Okay, so I think if you're ready, we can start. Our name of our next speaker is Brahim El Alaoui, and the name of topic is partition problem and defensive alliances in zero-divisor graphs of commutative rings.
Okay. So thank you so much. First of all, I would like to thank the organizer for giving me the opportunity.
I'm sorry to interrupt. Presentation got interrupted.
Does my presentation is?
Yes,
you can see my presentation.
Please share once again. So something.
Yes, there is no presentation right now. Please, can you share it?
I have to, okay.
Yeah, now we can see. Sorry,
And
continue.
now you can see my.
Yeah.
Okay. Oh, good.
I'm sorry, it's again got interrupted. There is no presentation again.
Okay. I don't know why, because when I click on the mode presentation, now you can see it.
We can see now, and it again disappears.
Oh, I'm sorry.
It's okay. We can maybe take a 5-minute technical break and.
Or maybe you can send in chat your presentation, and we will share it and we will show. Can you share your file in Zoom?
Or like this.
Or send it to our email by email, and I will share it.
Okay, but I think I can give the presentation in this form. Okay. Now you can see my presentation, I think.
Yeah, we can see. Yeah, and it's working.
It is clear or not?
Yeah, everything is okay.
We have to. Okay, good. Okay, first of all, I would like to thank the organizer for giving me the opportunity to share a part of our work in this wonderful conference. So my presentation is entitled Partitioning Problem and Defensive Alliances in Zero-Divisor Graphs of Commutative Rings. And this is a joint work with Professor Idriss Beniz from Mohammed V University in Rabat, in Morocco. So my presentation is divided in 3 parts. We start by the first one, in which we give a motivation and small introduction. The second section is devoted to the study of the partitioning problem. In particular, we study when the zero-divisor graphs of commutative rings are partitionable into global defensive alliances. And we finish by some references in the last section. So let's start by the first section. Actually, alliances are found in many varieties, including those formed by people who unite by kingship or friendship, by members of different political parties, in business by companies with common economic interests, in time of war by nations for mutual support, usually defensive, where allies are obligated to join forces if one or more of them is attacked. So this notion, I mean the notion of alliances in graphs, was first introduced by Christiansen, Hiditnemi in 2001. So, and then they define different types of alliances, namely defensive alliances, offensive alliances, powerful alliances. And these different types of alliances have extensively studied in the last decades by some researchers. Here we see some of them. And so in this work, we are interested in the first one. We are interested in the study of the defensive alliances in the context of zero-divisor graphs of commutative rings. So, but first, let me define what we mean by the zero-divisor graph of a ring and the global defensive alliances, and what we mean by partitioning a graph into defensive alliances. So actually, in this talk, R will be a commutative ring, and Z of R will be the set of zero divisors of the ring R, and Z of R star is actually Z of R minus 0. So the zero divisor graph of a commutative ring was first introduced by Anderson and Livingston in 1999, which is a sample graph denoted by gamma of R for a commutative ring with vertex set in the set of non-zero zero divisors, and two distinct vertices are adjacent if and only if the xy equals 0. Then to illustrate this kind of definition, we give the following sample example. So consider the ring of integers modulo 8, and so its illustrated zero divisor graph is given as follow. Here we have the set of non-zero zero divisors are 2, 4, and 6. And so here we have 2 times 4 is equal 0. So these two elements are adjacent, are as vertices. But here we have 2 times 6 is different from 0. So they are not adjacent. Okay. So now we define the global defensive alliance, which will be abbreviated as the GD throughout this presentation as the GD alliance. Okay, but first let me give some terminology and recall some terminology and notation. So let G be an undirected sample graph, and V be a vertex of G, S be the subset of S, then S be the subset of V, is a subset of vertices. Okay, so the open neighborhood of V is defined to be the set of U in V such that UV is an edge, and the open neighborhood of the subset S is defined to be the union of all open neighborhoods of its elements. And the degree of V is equal the cardinality of its open neighborhood. And its degree over S is equal the cardinality of its open neighborhood intersection S. Okay. Now S is said to be dominating if its open neighborhood is equal S bar, where S bar is actually V minus S. And the domination number of G, denoted by gamma A of G, is the minimum cardinality among all dominating sets. So now let me illustrate this last definition, I mean the dominating set. So by giving the following simple example. So consider the ring R, which equal the ring Z2 cross Z4. Then its illustrated zero divisor graph is given as follow. So then we have the green set right here. The green set right here is a dominating set of cardinality 2, since we have its open neighborhood is actually V minus S. And the yellow set is a dominating set of cardinality 3, and the red one is dominating set of cardinality 4, and the blue one is the whole graph, which is actually a dominating set of 5 vertices. So for the domination number right here, we have the green set is actually a dominating set of cardinality 2. So one can ask, is there any dominating set of cardinality smaller than 2? The answer is no, actually. When we take every vertex, its open neighborhood, it's not V minus the vertex itself. And then the cardinality of or the domination number of G of this graph is equal to. Then, and when the degree of x over s plus 1 is greater than or equal its degree over s bar, for every vertex x in S, then S is a defensive alliance set. And then S is said to be a GD alliance if it is both a dominating set and a defensive alliance set. So let's look back to our previous example and then determine either the previous dominating sets are GD alliance sets or not. So actually, if we take the green set, the green set is dominating set, but then let's check if it is a defensive alliance set. So we have here the vertex 1, 0. The degree of 1, 0 inside of the green set is 1, but the degree outside is 2. And then we have 1 plus 1 is actually greater than or equal to 2, which means that the inequality holds for the vertex 1, 0. We do the same thing for 0, 2, and we find that also 0, 2, the inequality holds also for 0, 2. We have the degree inside is 1, and the degree outside is 1. Then 1 plus 1 is greater than or equal to 1. And then the green set is defensive alliance set. But let's check for the yellow one here. We have the degree of 0, 3 inside. Here we have is 0, but degree outside is 1. Then we have 0 plus 1 is greater than or equal to 1. Then the inequality holds also for the vertex 0, 3. Similarly for the vertex 0, 1. But for the vertex 0, 2, we have the degree inside is 0, but the degree outside is 2. Then 0 plus 1 is not greater than or equal to 2, which means that the yellow one, it is not a defensive alliance, and then it is not a GD alliance set. And this proves also that GD alliance set, a dominating set, it is not necessarily a GD alliance set. Okay. So, and the GD alliance number of G, denoted by gamma A of G, is the minimum cardinality among all GD alliance set. So, since there is in this graph, since there is no dominating set of cardinality smaller than 2, then there is no GD alliance set of cardinality smaller than 2, which proves that gamma A of G of this graph of gamma of R is equal to, actually, is the cardinality of the green sets. So the problem of partitioning into GD alliances. So actually, in general, the partitioning problem is a very well studied problem in graph theory. It involves dividing the set of vertices into this is one subset or partition based on some specific criteria. So in this work, we are interested in partitioning the zero-divisor graph of a ring into GD alliances sets. And this problem has been previously studied for general graph by Erov, Gera, Shafik, Newton, and so on. And so so let's give first what we mean by partition. So for the graph G, let G be a sample graph and S1 up to Sn be subsets of V, where n is a positive integer. So the set S1 up to Sn is a partition of G. F, Si and Sg are disjoint for every I different from G, and V is equal to union of Si for I equal 1 up to n, with n is greater than or equal to then the graph G is said to be partitionable into GD alliances if it has a partition S1 up to Sn where Si are where the sets Si are GD alliances and N is greater than or equal to. So let's give a sample example. Consider the following graph right here. So here we give some different partition, but here the first partition, I mean A partition A, here we have the graph here is partitioned into two subsets, but into these two subsets are dominating sets, but they are not defensive alliance set, since if we take here, for example, the vertex V1, we have the degree inside of the set right here is 0, but outside is 3, and then 0 plus 1, it's not greater than or equal 3. So this is not a partition into GD alliance set. But this one right here, D, we have this set right here is a partition into in 3 sets, but it is not a partition into dominating sets. Since this one is not a dominating set because the vertex, this vertex right here is not in this set or not, and it is not adjacent to one of these two vertices right here. But these two B and C are two partition of this graph into GD alliance set. Okay. So the GD alliance partition number of G, denoted CG of G, is defined to be the maximum number of sets in a partition of V, such that each set is a GD alliance set. If we look back to these partitions right here, these two partitions right here, this is actually a partition into two sets, but here the partition, this partition here is a partition into three subsets, which are GD alliance sets. So one can ask, is there any partition of this graph into more than three subsets? The answer is no. If because there is no dominating set of cardinality smaller than 2. Okay, and then CG of this graph is 3. Okay, so G is partitionable into GD alliances if actually CG of G is greater than or equal to, and if it is not partitionable, we mean by that CG of G is equal to 1. And so here here we have CG of G is equal to 3. Okay. Now let's give the main results of this presentation. In this section, we study the partitioning when the zero-divisor graphs of commutative rings are partitionable into GD alliances. Okay, we start by the following subsection, in which we study the partitioning problem for local rings. Here we start by the following proposition, which gives a lower bound of the set of zero divisors of the ring R in terms of the GD alliance partition number right here, and this bound is sharp. We prove that using the following sample example. So consider the ring Z, the ring of integers modulo 9. And so this is its illustrated zero-divisor graph, and then the partition And then S1, S2 is a form of partition of the graph gamma of R into two GD aliens. Then CG of gamma of R is equal to, and so then we have CG of gamma of R square minus CG of gamma of
sorry
R.
to interrupt you. We are
Yes.
running out of time. Maybe in a few minutes, if you can wrap up.
Okay. Sorry. So then it is actually not clear how to determine the GD aliens partition number for any finite local array, but we can determine it for some specific cases. Here, the following proposition shows the case where R is finite local array with maximal ideal of index of nilpotency 2. And here corollary in which we determine CG, I mean the GD aliens partition number for the ring ZP to the 2. And as a second main result of this subsection, we determine the GD aliens partition number for ZP to the n for prime number P and the positive integer n greater than or equal 3. And here in this second subsection, we study when the zero-divisor graph of some kind of direct product of finite field are partitionable into GD aliases. And here we finish by some result in which we give a complete characterization for small GD aliens number and small GD aliens partition numbers. Here, for example, for finite ring where gamma A of gamma of R equal 1, so gamma of R is partitionable into GD aliases if R is isomorphic to one of these rings here. And when gamma A of gamma of R equal 2, then then the gamma of R is partitionable if and only if the ring R is isomorphic to one of this ring. And in addition to that, CG of gamma of R is equal to right here. And if when CG of gamma of R is equal 3, then R is isomorphic to the finite field F cross F4. And here we give some main references. So the third one and the last one are the principal references of this presentation. And thank you so much for your time. And I'm sorry for depassing the time of the presentation.
Thank you so much for the talk.